Okay, so the question at hand is what is this relaxation timescale lambda? Okay, so let me get another, yeah, okay, let me another page. So I said, what is the question? The question is something related to Deborah number, which is what is the relaxation timescale lambda. Okay. Now relaxation time scale can be understood in many different ways. Okay, and there are most of the ways are all the ways are all equivalent actually. But there is one intuitive way of understanding, and that is through the stress relaxation phenomena. So one way to understand is through the stress relaxation phenomena. What is the stress relaxation phenomena? Well, it sounds like a heavy name, but I promise you it is not. It's actually a pretty simple idea. So let us consider our previous problem, which was the example that we are considering, which is, let's say there are these two walls, and there is some material that is filled in here. Okay, and you apply a known amount of strain. So you move this wall to give the system a known amount of strain. Okay, and again, as I said, I'm discussing stress and strain in a sort of simplistic fashion that you are probably already familiar with, but we will discuss a more in-depth we'll gain a more in-depth understanding of stress and strain a little bit later. But right now you can just use your own intuitive understanding of stress and strain here. So let us say you apply a known amount of strain, and once you apply this known amount of strain, then you hold it constant. So apply a known amount, say epsilon naught, and hold it constant. Okay. Now what will happen is the strain is being held constant, but if you plot, sorry, let me draw it a little bit better. Okay, and here this is the time axis. Okay, and this is stress, tau. Okay. Just a second. Tau, stress. Okay, so we are looking at stress in the body as a function of time, and 0 here is after the stress is applied. So this is after, sorry, after strain is applied, after epsilon is applied and held constant. So once it is held constant, what is going to happen to the stress? See, if it is a fluid, you've already created whatever strain you had to. Okay, so the fluid, in case of a fluid, the stress has to decrease with time. But not so if it were a solid. If this material here, because I have not told you what material is inside, right? So if this material were something like a perfect solid, like let's say an idealized solid, then this material, to create this, to hold this strain at epsilon naught, you will need a constant stress. So if you had a solid here, then, or a perfect solid, then your curve would look something like this. It starts from some value, and this is for, you know, ideal solid. and it would be, you have to hold it constant forever. But for any real material, what actually ends up happening is it decreases with time. Okay. Now this decrease with time can be characterized by a certain time scale, and that time scale is called the stress relaxation or the just the relaxation time scale. So the stress in any real system would relax, will decrease with time, and there will be a characteristic time scale involved, and that time scale is called the relaxation time scale. Okay. So, for example, in some cases, this could be just an exponential function. So, this may be, let's say, for a certain type of material, it is something of the order of e to the minus t, but t is in the units of time, so you have to non-dimensionalize it. So, maybe this characteristic time scale here. So, now this becomes the characteristic time scale, and hence that becomes the relaxation time scale. So this is just an exponential decrease, and the characteristic time scale of this exponential decrease is the relaxation time scale. The exponential decrease is just an example. Okay, so this is just an example. It need not exactly be this so this is just an example. So for example, for some material it is like this, let's say. It could be other, the decrease could be characterized by other curves as well. Now, for the kind of fluid that we are discussing, or that we will discuss for the rest of this class, for us, this decrease will be almost instantaneous. Okay, so it will be so to hold the strain constant would require no extra stress. Whatever stress had to be applied, you have already applied. It's been done to create epsilon naught, and after that, nothing else is required. Okay, so let's say for an ideal solid, thus for an ideal solid, lambda tends to infinity. And for fluids, under discussion here, lambda is tending to 0, which means that the Deborah number is tending to 0. Okay? So that's the kind of fluids we are interested in. Basically, what this implies is, the physical implication of this is that when we are applying a shear force, the fluid sort of flows instantaneously. That is why most of the textbooks will write that a fluid will not withstand a shear force. A fluid cannot withstand a shear force, however small. So what they basically imply is that the moment you apply a stress, it starts. The flow in it starts instantaneously. Okay. So here I'm just trying to put things in perspective of a broader class, and there are obviously a huge class of materials where lambda is not 0 with respect to the observational time scale, and they look like fluids, but they will not be the kind of fluids that we are discussing right now. So there the Deborah numbers are not close to 0, and they can be for example, for example, if I egg yolk, that kind of material, it looks like a fluid, right? Or even the egg white, rather. Egg white is probably a better example. The egg white looks like a fluid, but it probably has a finite relaxation time scale. So if you are trying to observe a phenomena that is close to that, then you will have to consider a more elaborate scheme in that case. And the kind of discussion we are going to do for the rest of this class, that may not be sufficient, right? But do fluids really relax very fast? Well, the answer is yes. What happens in, for example, in a fluid like water, the relaxation time scales can be very, very small. Okay, it can be, I don't recall the value right at the top of my head, but I believe it's of the order of nanoseconds, or even less than that. So for any phenomena that you are observing in real time, where obviously most of the time the measurements are being done in seconds, minutes, hours, or flows like that, the relaxation of water itself is not all that critical at all. Okay. Okay, before I wrap up my discussion on Deborah number, one quick final thing, and that is just the quick perspective on the historical thing, which is the definition by Renner. Uh, there he said Deborah number, he used only D, but nowadays we use DE for Deborah number. He said that is lambda by T observation, right? Where lambda is the relaxation time scale of the material, T observation is the duration of the experiment. But in frequent usage, Deborah number is usually taken as lambda by a flow time scale, where T flow is a flow time scale. You need not bother with all this. We have understood these definitions. You will not, they are not critical for you unless you have a problem that you are solving that requires you to understand that, but not in the context of this course, obviously. For the context of this course, we understand now that we are talking about a material for with respect to whom the observer is calculating a Deborah number that is coming out to be close to 0. Okay. Okay. Okay, so now we can, there's one more important topic in chapter 1, and that just needs a little bit of discussion, which is fluid statics. Now, if you have a container and let's say it's filled with fluid, we know that the pressure, this fluid is basically characterized by this quantity called pressure, where this pressure is equal in all directions. That by itself is a very, very interesting fact or occurrence, and that happens because there is no underlying order to the fluid at the molecular scale, and that is why the pressure is felt equally in all directions. And apart from the pressure, in general the fluid, so pressure is something that is intrinsic to it, but apart from that, the fluid in general can encounter two types of forces, external forces. So in general, a fluid will encounter two types of external forces. One is surface force. So that's where the wall or an interface between the fluid and something else is going to have an impact. And the other is just the body force. Okay. And usually the only body force of significance is gravity. If you have a magnetorheological fluid, you can have magnetic forces. If you have there are circumstances where electric field can provide body force. that doesn't come in the scope of discussions for us, right? But you should know that, of course, there are many other types of body forces are also possible. So now, if this body of fluid was at rest, then the question is, what is the condition for equilibrium? To understand or figure out what that is, we need to consider a small differential volume here, right? So if we draw the differential volume out here, make it a little bit large, and let's say this is dx, this is dz, and this is dy, and the pressure at the center is P, then the force on this wall, or on this face rather, is given to you by now fluid is a continuum, right? That's what we discussed when we were talking about the continuum hypothesis. Continuum hypothesis basically lets you apply the tools of calculus to the problem through the assumption of continuity. So once we know that, what we can do is we can use the Taylor series expansion to calculate what the pressures are at the different faces. So at this face, the pressure, if I had to take force balance in one of the directions, I would take the force here as this is the y direction in which I'm trying to calculate the forces. So the force on this face for this differential element would be P plus del P by del y into dy by 2. This is the pressure. So to find the force, you just multiply it to the area. And similarly on this face, I don't have space here enough. So okay, this will be P minus del P by del y into dy by 2 dx dz. Right? So for a fluid which is in equilibrium, or if the fluid for fluid statics, you need summation fi's to be equal to 0, right? So now if you, on this differential element, what are the forces? For summation along the y direction, or the forces along the y direction, all you need to do is consider this force, and the body force, which I have not written down. Okay, so now interestingly, do remember that the pressure here always acts in the same direction. So once you start taking so on this face, which is along the positive direction, you have a negative sign, and here you have a positive sign. So when you do the summation, you will end up with, and I'm not doing it for you, it's this something you have probably seen earlier, you will end up getting del P plus del y plus Fy equal to 0. Right? There is obviously this term would have to be multiplied by the volume, so that will be dx, dy, dz, but that sort of would have cancelled out when you are taking the sums. So similarly, if you so this is, by the way, the body force, volumetric body force too. So similarly, if you do your summation in the other directions, you are left with not too many choices, but you will just get these other equations of x. Right? So this is the condition for equilibrium. Or rather, rather than the condition for equilibrium, I should say that in equilibrium, these equations will be satisfied. And we had already discussed that the general body forces are the gravitational body forces. So then the equation just, so if you know that the gravity is the only relevant body force, then you will just, these above equations will change into these. Gravity. Okay. Great. You must have seen this before, right? So you should be familiar with this. If you're not, maybe you just want to familiarize yourself with the UG UG level fluid statics for yourself one more time. I will leave you with a sample problem for you to do. And the sample problem is that of a tube dipped in liquid in an open container. So let's say you have a tube, and the tube is open, so that's why I have not closed it. And it's dipped in an open container, so there's fluid in here. And the fluid also has surface tension, so the fluid will rise up and attain an equilibrium height with the fluid. And this angle, let's say, is theta. And let's say this is diameter d. The gravity is downwards, take it as g. And then you have this height difference as delta h. Okay, I think, is that covered? No, one more thing I have to give you. So sigma, let's say, is the surface tension. So surface tension is acting on here at this location. So now the question is, find delta H in terms of all these other variables. And you can also assume, let's say, the density rho to be the density. Yeah, I think with that we have all the variables required. So can you relate delta H to sigma, rho, theta, delta and g? And the diameter here is also important, d. Okay, so we will stop here and we'll pick up from here in the next class. Okay.